Hello and welcome to the last lecture of MAE 229 for the spring quarter. Today I'm going to talk about RF MEMS, filters and oscillators, and there are a number of reference papers throughout the presentation today. There's one paper here that is a nice review paper that is from the IEEE Transactions on Ultrasonics, Ferroelectrics, and Frequency Control. It's by Professor Clark Nguyen from UC Berkeley, and a number of the references throughout this paper and some of the slides are actually from Professor Nguyen as well. And I'll comment that for those of you who aren't taking the course this quarter, there is a new course in the ECE department that is entirely about RF MEMS. And so that would be sort of a natural next course to take if you find that you're interested in this subject. So you may not know it, but inside your cell phone there are a lot of discrete electronics, meaning that they are little individual chips. And it turns out that one of the reasons why there are so many individual chips in your cell phone is that a lot of the functions in a radio actually cannot be done with a silicon chip. And so in this diagram you can see there's a section here that's sort of circled in gray. And this would be the electronics that would be on an integrated circuit. And so it's sort of indicated with this box here. It says transistor electronics down here. And it's not really important that you know what all these things are. This LNA is a low noise amplifier. The VCO is a voltage controlled oscillator. But these things are all made with transistors. But the problem is that, like it says on this slide, the first bullet point, is that high Q functionality required by oscillators and filters cannot be realized using standard integrated circuit components. And so off-chip mechanical components are used. And so you remember Q means quality factor. And in MEMS devices, right, if we have a high Q, that means we have a very sharp resonant peak. And so that's the same thing. That definition of Q is used in the same way for integrated circuit filters. It just turns out that at radio frequencies, it's very hard to make an inductor and a capacitor that have low series resistance. And if you remember from our electrical models of resonators, it's really that series resistance is part of what determines the quality factor. So if you want to make a narrow band filter, a sharp filter, you need to have a high quality factor, and you just cannot do that at radio frequencies with inductors and capacitors. And so as a consequence, if you go back to now looking at this board, all these other chips that are on here, so here's this one that's made with a silicon die, and it has all kinds of complicated stuff on it. But for each of these filters that's in the radio, they're actually made with a discrete chip, and it says here they're ceramic. So there's the antenna here. There's a first sort of narrow bandpass filter, right? This waveform is passing through, and the other ones are filtered out. That's a SAW filter, surface acoustic wave filter. And then the signal goes into the electronics. It actually comes out to be filtered again at intermediate frequencies, so that it's sort of demodulated from the original high frequency to a lower frequency and intermediate frequency. And again, it has to go through a mechanical filter, a surface acoustic wave filter. It goes back to the circuitry where it's processed and then demodulated to possibly an even lower frequency. And there is shown here, it's a crystal intermediate frequency filter. So again, that's a mechanical resonator. So each of these guys that's sort of here is a discrete mechanical resonator. And then what's shown here is a crystal oscillator. So the thing that generates the timing frequency, the thing that actually generates all the, what tells you what is 100 megahertz, is a crystal, a quartz crystal that's in a nice metal can here. And so as cell phones get to be smaller and smaller, and actually, they are multi-band phones, they need filters at all these different bandwidths. Basically, it ends up being that you need a lot of these discrete parts. And, if you want to make a cell phone small, you really wouldn't like to have these things. So like it says here, SAW, ceramic, and crystal resonators really pose bottlenecks against making cell phones smaller and incorporating radios and things that are, other than cell phones. Putting small radios into all kinds of devices, right? And so we know that now kind of more and more things have wireless transceivers on them, maybe even your toaster. And so making those radios small is going to require some way of eliminating a bunch of these discrete SAW filters, for example. And so if you look at this diagram, it's another kind of wireless system, very similar sort of idea about like the cell phone shown here. But now essentially what's shown is that all the elements that are in green here are some places where MEMS could actually play a role in this in this cell phone. And again, you see the reference for the paper that this came from Professor Clark Nguyen. And it's not really important that you know what all of these things are. There are filters that are shown here, intermediate filters. There are some switches here. So there are some configurations for phones where you have a transmit and receive switch. So you basically switch from it's kind of listening, so receiving signals, and then you switch to the receiving signal path is here, and the transmit path is here. And so you can use you'd like to use a very low insertion loss switch, meaning that the signal that goes through isn't there's no loss in that signal, and you have high isolation, so that when you are receiving the receive signal, which is probably a very small signal, you're very well isolated from your transmitter, which is blasting away at maybe a watt of power or so. So this is actually normally done. It's not important how it's done right now, but you could imagine doing this with kind of a relay switch. Relays are too big, it turns out, for this application, and so it would be really nice to have a little MEMS chip that could be able to do this. And I mentioned, multi-band phones. So, if you have a world phone and you might want to use like a CDMA network here, like if you're using Sprint in the United States and you want to go to Europe, then you're going to have to use actually a different radio to do that. And so if you have a phone that's a world phone, your phone actually has many different radios inside it to be able to operate it with these different standards. And you actually need a different antenna that's optimized for that different radio. And so there may be multiple antennas in your phone already. And so you'd like to select between those antennas. And so again, you'd like to do that with a switch. You'd like to do it with a small switch that has high electrical performance. And so there's yet another opportunity for there to be MEMS devices in these phones. I'm not going to talk about switches today. There are also, you see some here, some just pure passive. So there are capacitors and inductors. The reason these are here is you'd like to, for many applications, you'd like to have a capacitor that you can tune, that you can adjust it. Same thing with an inductor. And so there are MEMS ways of making these tunable capacitors and tunable inductors. In fact, there's a company called Weispry. Their whole business is making MEMS tunable capacitors. And if you're interested in learning more about those things, then you could, for example, go to the Weispry website or look up some papers on those things. I'm not going to talk about them today. So just kind of give you a picture. This is like a band select filters. Existing filters, for example, there are this IF filter, intermediate frequency band, that's 240 megahertz. And so this is a picture of an IF filter. This is it's usually what's called a surface acoustic wave filter or a SAW filter. I'm not going to talk about SAWs today, but there are many books, for example, about SAW filters. You can Google SAW filter and you'll find lots of information about them. It says here bulky, and you might think to yourself, this is like 4 by 4 millimeters, and that seems kind of small. But if you have to have a bunch of these things, then you could easily see that that's going to fill up your whole iPhone. So they have a Q of about 1,000, and so this is like a reasonably high performance device, and it kind of meets the specs that are required. And so really the problem that needs to be addressed is you'd like to be able to make something that was smaller than this device. The RF filter, this is an example of one. This is now, sort of right after the antenna, before the first demodulation. This particular one is 868 megahertz, Q of 1500. So this kind of gives you an idea, like quality factors that they're talking about in these filters are on the order typically of about 1,000 to 2,000 for existing parts that are in phones. And actually, so this is 868 megahertz. It turns out that, like, for example, in the United States, one of the very interesting cellular bands is actually at 2 gigahertz. And so some of these RF filters are operating up at 2 gigahertz with quality factors about 2,000. And I mentioned quality factor. Quality factor is what determines both the width of this, actually this is sort of a bad color to use. So this is a picture of the frequency response of one of these filters. This is the IF filter frequency response, and so here's frequency in megahertz, and here's that center frequency at 240 megahertz, and you see there's this nice sort of narrow window here where the attenuation in dBs is close to 0. So that means it passes all the signals that are in this sort of narrow band here at the peak. Okay, very narrow frequency here, and it's saying this is delta F here. It's saying on the side is 260 kilohertz. So F naught is 240 megahertz. Delta F is 260 kilohertz, and you notice that that is the width of this thing, delta F, is equal to F naught over Q. Okay, right. So it's the resonant frequency divided by the quality factor is what determines the full width of this passband. Full width being the full width of the resonance, and that's actually at the minus 3 dB point. So minus 3 dB from the peak. Okay, and that's minus 3 dB. It turns out is half power. That's why we use minus 3 dB. So the signal is at half the power when it's at the spans of delta F here. Okay, so why use MEMS? So the advantages are that you can have very high quality factor in MEMS devices. So quality factor of 1,000 is probably easy to do. 10,000 is also possible, kind of depending on what frequency you're operating at. So you can have very high quality factors, and certainly compared to pure RC circuits, that's really fantastic. You potentially can have low loss, meaning that the signals pass through more or less at the same amplitude. So you can make things like filters, phase shifters, variable inductors, variable capacitors, and switches. Having tunability and reconfigurability, as I mentioned, is useful for inductors and capacitors, and then switches, clearly they allow you to reconfigure things so you can select different antennas. Low power consumption, very important in portable devices. If you want to put a radio, I gave the example of your toaster. Obviously, your toaster is plugged into a wall, but there are many other things that you might want to put a radio in. Even, let's say, medical devices, and maybe even implants, right? And so those things, you'd really like them to have components that have low power consumption. And so electrostatic and piezoelectric actuation for MEMS devices are very attractive for that reason. Now, so what makes this hard? First thing is that radios are fast, right? We're talking about things that are operating at 1 gigahertz, 2 gigahertz, and so the speed that's required for some of these things is quite high. So the transmit-receive switch, you've got to be able to switch pretty fast. You've got to be able to do that a lot, a large number of cycles, and so you want to make sure that the thing is very reliable. And so as I mentioned, then operating RF frequency. So for these RF filters, I mentioned that the kind of a dominant cell standard in the US is at 2 gigahertz, and so it's quite challenging to make a mechanical device that operates at 2 gigahertz, but it's possible. Reliability, I mentioned, right? So that, for example, in the case of switches, in particular, reliability is quite a difficult challenge because you have contacting parts that you might actually be flowing current through those things. And so that's kind of an area of active research. Packaging, whenever you have a moving mechanical device, right, you're going to have kind of a special package that's not typically used for an integrated circuit. And so packaging can be expensive, and the idea is that all these things you'd like to be able to make them small and low cost, and so that packaging thing, has to be solved. And then the last thing is integration. So if you could, in that very first slide I showed, there's this one silicon chip and there's all these other little discrete packages for the filters, and so certainly there is a vision that if you could make all that stuff on silicon and make all those filters on silicon, then you'd suddenly end up with just one chip. So that's quite an attractive proposition because you could have a radio that is basically like a single chip radio. There are single chip radios that exist. They're not the kind of high performance radios that you'd use for a cell phone. But that's kind of one vision for the future, is that you could have something where you have this multi-band radio that has all kinds of nice micromechanical filters in it, and wouldn't it be nice to be able to do that all in silicon? So that's the vision. That's basically going to kind of set the context for why people are interested in RF MEMS. So let me start off then with the very basics. So we'll talk about micromechanical resonators. And we've talked about some of this before. But the idea is high Q resonators. So why do you care about Q or quality factor? This picture shows an example of an oscillator, actually. So what it is that down here, this is our micromechanical resonator, right? And it's modeled, we can think about it as a mass spring damper, but it's modeled by its equivalent LCR components, right? Remember, this is sort of the mass, the spring stiffness, and the damping of this resonator. And so this guy has a characteristic resonant frequency, square root K over M for mechanical engineers, or square root 1 over LC um, for electrical engineers. So it wants to sort of oscillate at that frequency. And if we put it in a positive feedback loop with an amplifier here that has some gain to it, what will happen is that this circuit will oscillate at that characteristic frequency provided that the phase shift around the loop is equal to 0 degrees. So it turns out that at resonance, so sort of showing over here, if we looked at the magnitude and phase frequency response of just this LCR resonator thing, it looks like this. It has a big peak at the resonant frequency. So this is showing like a 10 megahertz oscillator. So it has a peak here. And then if we look at the phase response, it actually goes from, at low frequencies, it goes from plus 90 degrees to minus 90 degrees at high frequencies. And so at the resonant frequency, the phase shift of this LCR thing is 0 degrees. Okay, so so there's 0 degree phase shift at resonance. And so if we put this into a feedback loop with an amplifier that has no phase shift there, it will actually oscillate. It will lock to this resonant frequency and it will oscillate. And that's what this waveform is showing here. This circuit here with what's called a sustaining amplifier will oscillate at the characteristic natural frequency of the resonator element, right? So either we could think about that as omega naught is equal to square root K over M, or we could write it as 1 over square root LC, right? For the electrical parts. And T naught here is the period of the resonance, right? So we have T naught here is equal to 1 over F naught, or we could write that F naught is equal to omega naught over 2 pi, okay? And so there's two scenarios that are shown here. We have a resonator that has a quality factor of 10 on the left, and on the right there is a resonator with a quality factor of 1,000. So this is like a kind of a crystal oscillator. Actually, crystal oscillators, quartz crystal oscillators, typically have a quality factor of like 10,000 or more. But you can see the difference between these two things is that the width of the resonance is it's a lot broader when Q equals 10 than it is when Q equals 1,000. And if we look at the phase response, it's a very sharp phase frequency characteristic for the high Q oscillator, and it's a very sort of shallow slope for the low Q resonator. And so one way that we can conceptually think about the importance of high Q is that if there's a little bit of phase shift fluctuation in this loop, say the amplifier has a little bit of phase fluctuation like jitter in it, then that fluctuation, here's an example, let's say that it's 40 degrees, which is quite a large amount of fluctuation. There's a very small change in the frequency here of this resonator, okay? So the frequency at which this guy is going to oscillate, remember it wants to oscillate where the net phase in the loop is equal to 0. So if there's a little bit of a phase shift here, let's say 40 degrees in the amplifier, then we're going to basically oscillate if we have the net phase shift equal to 0. So if it's minus 40 degrees here, then we're going to have plus 40 degrees in the LC circuit. And you can see that that results in a very small change in the oscillation frequency. So there would be basically a change in frequency of 4 kilohertz for this high Q oscillator. Whereas if we look at the low Q oscillator, right, if we imagine shifting by 40 degrees to keep the net phase around the loop equal to 0, then we see that there's a 400 kilohertz change in the frequency. And that's a big deal, right? If you're trying to make something where where you have a radio or some other key, very important timing application, then your reference oscillator, if it's a 10 megahertz oscillator, which is kind of a standard frequency for these reference oscillators, you really want to know that it's exactly 10 megahertz. And 10.4 megahertz, right, which this would be, or 9.6 megahertz, is not going to do it. Whereas if you look over at this guy, then you'd have 9.96 megahertz. Oh, I guess it's 9.996 megahertz. Right, so you have 100 times better frequency stability. So one reason that you want to have very high Q is in timing devices. You want them to have a very exact frequency characteristic. You want them to oscillate exactly at, in this case, 10 megahertz. And so you better have a very high Q element to be able to do that. So the problem is that if we are using real inductors and capacitors, LC tanks, like it's said here, you cannot achieve a Q in the thousands. So on-chip spiral inductors, they're made with spirals of metal, and so there's a lot of series resistance in those spirals. And so the quality factors of those spiral inductors is no higher than 10. And off-chip inductors, so if you wanted to use a kind of a discrete inductor that's not made on a silicon IC, still the Qs are only about 100. So you cannot make a high Q oscillator using electrical components at 10 megahertz even. So many years ago, people recognized that vibrating mechanical resonances can be very high Q. So Q greater than 1,000 is possible. So quartz crystal resonators are kind of the standard. They have extremely high Qs, so a Q of 10,000 or higher. So like the crystal oscillator that's in your watch, for example, right? Everybody has a quartz watch, I'm sure. So that typically has a Q of about 50 or 60,000. It's a very high Q, and that really is what guarantees that your watch works so well. That's why the timing accuracy of a quartz watch is so fantastic, and why nobody has a mechanical watch. And Q of 1,000,000 is certainly possible in quartz resonators. And the most common kind of quartz oscillator works in what's called a thickness shear mode, or a TSM. Sometimes you'll see it like this, thickness shear mode. And so how does this work? Well, here's a picture of a piece of quartz, and it has electrodes on the top of it, okay? And so we're imagining that we have like a voltage. This induces some electrical field here in the quartz, and there is a piezo coefficient which I can't remember the name for, but it's like D44 or something, that generates shear, right? So there's shear, and that, if you remember from the lecture where we're talking about shear basically results in kind of the sliding motion of these two faces, like this. So this is called a thickness shear mode, right, where we have electric field going through the thickness of the quartz, and that results in a mechanical shearing motion. And that turns out to be a very high Q kind of resonance, okay, very high quality factor. So this thickness shear mode oscillator, if we looked at its electrical equivalent circuit, it just looks exactly like this. It's got the motional inductance, motional capacitance, motional resistance, and the quality factor of this resonance is going to be more than 10,000. This C0 here represents the pure electrical capacitance, and so if we just look at the area of these capacitive electrodes and the thickness of the quartz, right, we can imagine this thing looks like a parallel plate capacitor that's filled with the quartz dielectric, and so this C0 is the purely electrical component. And so this would be basically epsilon, where epsilon is the dielectric constant of the quartz times the surface area of the electrode times the thickness of the quartz. Right, and so this is typically, you know, for thickness shear mode oscillator. It really depends on the particular oscillator that you buy, but it's on the order of a picofarad or so, just to kind of give you a scale for these things. Okay, so to remind you a little bit about resonator equivalent circuits, way back when we talked about this comb drive actuator, and it says here it's a 2-port lateral microresonator, and here's the physical structure of the device. So you remember it's got these little spring suspensions and it can move back and forth. It's called a two-port because it has this. This is the input port here, port 1, and there's an output port, that's port 2, right? So if this was a one-port, resonator, I'll just kind of schematically draw it, right? If it was a one-port, we basically kill this part, and we only have this one port at the drive input. And of course, there's a ground somewhere. So we would really have two terminals on this device. One way we can think about that is we have this DC bias pin here. Okay, so there are such things as one port resonator structures. This particular one happens to be a two-port. Okay, and so the picture is what's as shown here. So we actually apply a DC voltage to the moving part of the structure, right? And there are small signals, so that's why this VP is a big capital letter, because it's a DC bias. And then there are these small signal inputs. V sub I is a small signal input, and V sub O is the sense output. And so you may remember that we made an equivalent circuit for this guy, right? So if we think about this, like from when we very first talked about this guy, we would draw a picture like this with a nice transformer, right? And we had an R and a C and an L, and then we have another transformer. So this like goes back to, I think, oops, this goes back to probably homework 2, I think. Okay, and so we have, I'm going to call this again, I'm going to call it VI here, and then we've got a current. I'm going to draw it this way, I out, like this. Okay, and then we had the, this is the motional resistance here. This is the, actually, you know what I'm going to do is I will give them their mechanical names, right? So this is really the mechanical domain, right? This is electrical, right? And so we get an input force here from the transformer. The transformer converts the input voltage into a mechanical force. And then we have a velocity going across these guys, so I'm going to call this x dot, like this, right? Remember this, if we imagine the resonator moving with some velocity x dot, like that. And so the transformer here, it's like a step-up transformer, 1 to eta, and then we're stepping back down here, eta to 1. And so we can imagine basically this transformer takes the input voltage, converts it to a force. This transformer takes the velocity and turns it into a current, okay? And then we had, this is the damping, this is the 1 over the spring constant, and this is the mass, right? So that's inductor has the mass, right? And it turns out, so if we write like this, F is equal to eta times Vn, and I out is equal to eta times x dot. Okay, and it turns out that eta is equal to dc dx times this DC bias, the polarization voltage. Okay, dc dx is the change in capacitance. It's basically this capacitive sensitivity, right? It's the derivative of the capacitance with respect to displacement. Okay, and we derived this way back when. If you can't remember, look back at your notes. And so then, way back on the homework also, we sort of showed that we could get rid of these transformers and convert these mechanical elements into equivalent electrical elements. And so R equivalent, L equivalent, C equivalent are given like this. So R equivalent is equal to B over eta squared, it turns out. L equivalent is equal to the mass divided by eta squared, and C equivalent here is equal to eta squared times 1 over k. Okay, and so it will turn out. Okay, so actually I do have another blank slide that we can go over this with. So these other things that are on the diagram here there's some additional elements, right? The basic inductor, the basic resonator components are these guys. We've talked about them many times before. There's also, if we look at this, there's C naught here, right? There's really an electrical capacitance that the drive signal sees. Okay, so there's a true electrical capacitance C naught. Okay, and similarly on the output transducers, and these are the same value because this guy is symmetric. If we look at the layout, right, we can see that the input capacitors look like the output. Sorry, the input capacitors look like the output capacitors. And so these C naughts here represent the electrical capacitance seen at the input and output terminals. C int here is the interconnect stray capacitance. So there's some capacitance between the interconnect used to we're going to run some signals, presumably possibly even off chip to this device, and so there's some interconnect capacitance to the substrate, and these are kind of drawn as being the same here. So if this had like identical routing on those traces, then that would be true. And then there's also some resistance in the interconnect, so R interconnect here. Typically, this R equivalent here, the motional resistance, is going to be a lot bigger than the interconnect resistance. But if we design the MEMS structure very well, and we happen to be lucky that we have a very good MEMS process, then it's possible that these interconnect resistances might be significant. And so we have to be careful about those guys because um, it turns out that they can contribute to reducing the quality factor of the resonator, okay, because they're just in series with the motional resistance here, okay. And so, let's see, let me take a break for just 1 minute.